In this video exercise, we will demonstrate how to run a protein-protein docking calculation where one protein is treated as the receptor and the other as the ligand. In the general case, it doesn't matter which protein is treated as the receptor and which protein is treated as the ligand, but for antibody-antigen docking, the antibody is the receptor and the antigen is the ligand. The docking is performed as a rigid body optimization, and there is no subsequent minimization of the interfacial region. With that in mind, let's begin. The receptor used in this exercise is 1QQU, shown here, while the ligand is chain B of 1BA7, shown over here. Both of these proteins have already been passed through the protein preparation wizard and are ready for protein-protein docking. Now, although it is not necessary to prepare proteins for docking, it may be advisable to do so, as proteins from the PDB often do not have coordinates for side chains on the surface of the protein, or even for whole chains that are solvent exposed, as these are usually more mobile and can be difficult to determine their coordinates from the X-ray data. If these missing parts of the structure are not in the favored binding region, the docking should still produce good results. However, if the poorly defined parts of the structure are in the binding domain, then running the protein preparation wizard can improve the results. With that in mind, let's go to Tasks, Protein-Protein Docking. We'll choose Standard in the Mode section. This mode is used for docking a protein to another protein without any special conditions on the type of protein. If we were docking an antigen to an antibody, then we might want to add special conditions such as preventing the docking to the non-CDR region. And if we wanted to dock a protein to itself to create a dimer or a trimer, then we'll use these options. Now here, we'll choose the receptor and ligand. First, we'll make sure that 1QQU is included in the workspace by removing 1BA7 from the workspace. Then, for the receptor, we'll choose from the workspace since 1QQU is now in the workspace. Now you'll notice that we could have also chosen a file or automatically retrieved the PDB, although in that case, the protein will not have been fully prepared via the protein preparation wizard. Next, we'll repeat the process for the ligand, making sure only 1BA7 is in the workspace. We can then view both proteins in the workspace by clicking this icon here. There are two parameters to control the docking here. The first is the number of ligand orientations to the receptor that are sampled. You can set the value here in the number of ligand rotations to probe. The maximum value is 70,000, which corresponds to approximately sampling every 5 degrees in the space of the Euler angles. Decreasing the number of rotations generally degrades the results, but shortens the runtime. The second parameter is the number of poses to return. Each pose represents the center of a cluster that results from the clustering of the top 1000 results of rigid docking of the ligand. If more clusters are found than the number of poses to return, the clusters are ranked by size and the poses are chosen from the largest cluster. If fewer clusters are found than the maximum number of poses to return, one pose per cluster is returned. Over here in the constraints section, we have the option to add constraints to the docking process. For example, you can provide an additional attractive term to the potential, remove the attractive potential, or declare residues to be buried for residues that are specified. Constraints are implemented as a bias during the docking process, so they increase or decrease the likelihood of the specified interaction, but do not guarantee that the specified restraint will be met by all top-ranking poses. For example, let's assume we know in advance that arginine 63 and arginine 65 on 1BA7 bind at the interface of 1QQU. We'll make sure the constraint is set to attraction, protein is set to ligand, since 1BA7 is our ligand here, and then we'll head to the workspace. We'll click R on the keyboard to change the selection mode to residue, and then shift-click the arginine 63 and arginine 65 in the workspace. And then now we can simply choose from workspace selection as the residues to specify for the constraint. Now for the bonus, this defines the increase in the attractive potential for the attraction constraints. The value must be in the range 0.11 to 0.99. And then this value is added to 1 to define a scaling factor for the attractive potential. In this example, we'll just leave it as the default. Okay, once we have everything set up, we can rename the job and then click Run. The job can take up to 4 hours on a single processor. Once the job finishes, the results are incorporated into the project. First, we'll click the All row in the toggle table and choose Remove Everything from Workspace. This is just to ensure that we are starting with nothing displayed. Then we'll click Include in Workspace, and here we can select the receptor, which is 1QQU, and then we can select the ranked ligand poses, i.e. 1BA7. Here we'll select the first ranked pose, and then click OK. Now, it just so happens that there is a crystal structure of this complex, although it does contain a couple of different mutations. That protein is 1AVX. I've already pre-aligned chain A on 1AVX onto 1QQU, which should allow us to directly compare the pose of 1BA7. Now, it's clear that the top predicted pose did bind into the same region as seen in the reference crystal structure, so this is not a bad result. However, the docked pose is displaced and rotated somewhat from the reference. This is clearly due to the docking algorithm, because the pose should be exactly over the reference ligand if the docking was perfect. Ultimately though, this shows the level of accuracy you can expect from protein-protein docking.